All right, let's get started. Welcome to Ali Martz, who's going to talk about Python for the early stage design of sustainable aviation fuels here in the general track. Thank you so much.
Thank you. My name is Ali. I am a graduate research assistant at Oregon State University under Kyle Niemeyer. We collaborate with VRAP and her team at Lawrence Berkeley National Lab with funding provided by the U.S. Department of Energy's Bioenergy Technologies Office. Good morning, everyone. We are making a cake recipe. Now, we have a few goals in mind while accomplishing this. We want it to taste good, obviously. We also want it to be inexpensive. We're not trying to break the bank here. We got lots of other hobbies we would rather spend our money on. And then we also want it to look nice. Like, maybe it's just me, but I don't want to eat a cake that does not look appetizing. So as you can see from these three examples, they all are, by definition, cake. However, they satisfy our goals of taste, cost, and appearance in very different ways. So we have that chocolate ice cake on top where it looks nice, it's a fine cake, but it is a little plain. It looks like a box mix from the store though, so that's great for our wallets. And then as far as the taste goes, it looks like it could be a little hit or miss to me. Maybe that's just my opinions. But then if we look at the pink cake below it, it looks a little cleaner, it looks a little nicer, it's pretty. The little embellishments on top might make it cost a little bit more, so there's that consideration. And then as far as the taste, it kind of looks a little dubious to me as well. And then you have the one on the right, which is gorgeous. It has 10 out of 10 visuals. It's stunning, but you also know that that one is going to be really expensive. And will it taste as good as it looks? I have my doubts. So evidently, this is a problem that's a little more difficult than it first appears. So why is that? Well, first, we're looking at a multi-objective problem. We are considering taste, cost, and appearance all at the same time. And furthermore, these three things are not mutually exclusive. They conflict with each other in ways that aren't always readily apparent. And so that's going to have a lot of interplay when you're designing your cake recipe. So for example, we can make our cake taste better by using higher quality ingredients, but that is absolutely going to make it more expensive, which is what we don't want. There's a conflict there, and there's going to be a trade-off involved. Furthermore, using higher quality ingredients could affect our appearance in ways that we don't understand right now, and we won't be able to foresee until later in the process. This is also a multi-parameter problem. Technically, you could make anything a cake recipe ingredient if you're brave enough. That being said, I don't necessarily endorse or recommend that. But there are a lot of different things you can include to make a cake, such as like flour, sugar, and eggs. So there's an entire process involved about picking the correct ingredients, understanding how they interact, and then choosing the correct proportions of each. And then furthermore, flour, sugar, and eggs are pretty basic cake ingredients, and there are a lot of different cakes that you could make out of those three. And not all of those cakes may meet the taste, cost, and appearance objectives that you're looking for. So this evidently is an incredibly complex problem, but Ali, why are we talking about cake on Wednesday morning? Why is that important? Why does it matter? Well, we can apply this cake analogy to multiple real-world scenarios. One is accelerating the manufacture of pharmaceutical disintegrating tablets. There are many production pathways to make these tablets, but not all of them are going to be suitable for full-scale production and manufacture. If we revisit our cake analogy, this is like how we can have ingredient combinations that are just going to give you a completely inedible cake that no one's going to want to eat. So as a result, it's very important to eliminate poor production pathways or poor ingredient combinations from the outset. Another example is battery design. Again, similar to our cake analogy, there are lots of different parameters to consider when designing a battery. For example, the materials you're using in your cell or how you're arranging them. And so it's very important to key in on those really important parameters first before you start figuring out the specifics of them and the optimal values of them. So again, like our cake analogy, that's us choosing what ingredients are going to make our very tasty cake, and then from there figuring out the proportions of them that we need to use. So these examples and this cake analogy indicate that multi-objective, multi-parameter problems are extremely complex. And there are standard optimization solvers out there, such as SciPy Optimize, that are really powerful tools and are suitable for a lot of different optimizations. However, they're not necessarily designed for this level of complexity and this much freedom and variability in the search space and this many options and possibilities. So we seek to develop a methodology to address this, and to do so, we transfer our cake analogy to transportation decarbonization. So different modes of transportation are going to have different decarbonization pathways. For example, gasoline vehicles are often decarbonized by converting them to electric vehicles. We specifically focus on aviation. This sector accounts for 2 to 3% of global carbon dioxide emissions, and it's very difficult to decarbonize. One reason for this is that flight just requires a lot more energy than other forms of transport, like cars and buses. So it needs a very energy-dense fuel in order to actually support this gigantic monstrosity of an aircraft going hundreds of miles per hour, tens of thousands of feet in the air. We currently achieve energy-dense fuel with conventional aviation fuel. It is a liquid petroleum-based fuel, and most importantly, it has very stringent requirements with properties such as freezing point, flash point, viscosity, and density. And this is to guarantee that your fuel is going to be safe for flight. A specific example of this is your conventional Jet A has a freezing point of between -42 to -47 degrees Celsius, and that is to make sure that your fuel lines are not going to freeze when you're at cruising altitude at 20,000 feet, because that would spell very bad news for the people and the cargo on board, which is not what we're looking for. Because of these factors and fuel requirements, sustainable aviation fuels are the primary decarbonization opportunity for long-distance flights. These fuels are derived from biomass feedstocks, such as cooking and plant oils or agricultural residues. And most notably, they are designed to have a comparable performance to conventional fuel. And again, that is for the safety of people, the environment, and sustained flight. However, implementing sustainable aviation fuels is a lot trickier than it would first appear. First is the cost. Sustainable fuels are very expensive to make. An example of a production pathway is here on the screen. There are additional steps associated with obtaining, processing, and transporting your biomass feedstock. And one consequence of those extra steps and the cost associated with them is that the volume of sustainable fuel that is produced today is not nearly enough to meet market demand. As such, it's not economically competitive with conventional fuel, and it's just not possible to scale up production of sustainable fuel in order to fully replace conventional aviation fuel. Sustainable aviation fuels are also just slow to develop. One reason for this is the fuel certification process, and this is something that any fuel must do in order to fly. And that, again, is to ensure that it will have the correct properties, such as the previously mentioned freezing point, flash point, density, and viscosity for safety and performance considerations. Now, fuel certification is a very lengthy and resource-intensive process. It requires estimates of 3 to 5 years, thousands of liters of fuel, and millions of dollars. Candidates that don't have the correct property values in certification are either abandoned partway through the process, or they require even more resources and funds to correct. Now, this is particularly relevant to sustainable aviation fuels because biomass feedstocks introduce a lot of variability into the production pathway. And there are examples of researchers ideating this biomass fuel and designing the entire production pathway, and they're like, this is great, this is exactly what we're looking for, it'll give us the exact properties we want. And then only when they start to actually physically do that refining process do they realize that somewhere along the line, one step of it had an effect on one or more properties that they weren't able to predict. And now those properties are completely off from where they want them to be, and they're so far off that there's no way to correct that, and they just have to scrap the entire thing and start over again from scratch. So accuracy in anticipating property values is very important to developing new candidates. So then that just raises the question of how do we do it? How do we ideate new sustainable aviation fuels? Our answer is to create an optimization tool for the early stage design of novel sustainable aviation fuels. We aim for this work to reduce the resource requirement of aviation fuel certification and accelerate the replacement of petroleum-based jet fuels. Our methodology to do this is a sequential optimization. So using target values for properties and possible fuel components, we identify the optimal blend that best achieves those said target values. Revisiting our cake analogy, this is like making our recipe from assorted ingredients for our target objectives of taste, cost, and appearance. Also, like our cake analogy, the possibilities for sustainable aviation fuel from a pool of components is incredibly large. We're considering not only the ways to combine all of those components, but also their ratio permutations. So this leads to a very large and complex search space, and we have to reduce it and narrow it down in order to efficiently and effectively solve this problem. And so we reduce our search space to the best performing component combination. From there, we identify the optimal blend ratio with a multi-objective Bayesian optimization. We use open source Python-based packages, BoTorch and Ax, to help us do this. And what we get at the output of this methodology is an optimal blend ratio of the components we obtained from our search space reduction. So first, let's explore a few more details about this sequential optimization. So again, first up is our search space reduction, where we narrow down the possibilities. This, in our cake analogy, is akin to picking the ingredients that we're including in our recipe. So first, we generate combinations of ingredients. So for example, we have combination C1 of cake flour, sugar, and oil, and combination C2 of bread flour, salt, and eggs. And then next, we discretize recipes. So an example of that for our bread flour, salt, and eggs combination would be something like 2 cups of bread flour, half a teaspoon of salt, and 3 eggs, or 2 cups of bread flour, a quarter teaspoon of salt, and 2 eggs. And so once we have all of these discretized recipes, we then can predict their objectives. Again, that's our taste, cost, and appearance. And once we have those predictions, we then organize and sort them with Pandas, and we identify the ingredient combination that gives us the best performing objective predictions. And then that is what we export to the next step of our process. But first, translated to sustainable aviation fuels, our ingredient combination becomes something more like Jet A, tetralin, and toluene, or Jet A, tetralin, and cumin. And then our discretized recipes become discretized fuel blends. So instead of like 2 cups this, teaspoons, and numbers, it becomes something like 10% Jet A, 10% tetralin, 80% cumin, and then the same components, but at a 10-20-70 mix or a 10-30-60, et cetera, et cetera. The Bayesian optimization part of this methodology in our cake analogy is where we optimize the proportions of the ingredient combination we just got from the last part. And in sustainable aviation fuels, that's pretty synonymous. We are optimizing the blend ratios of the components that we received from our search space reduction. Now, we specifically chose Bayesian optimization to do this because it is specifically designed to optimize complex, computationally expensive problems where little to nothing is known about the underlying relationships. If we take a closer look at this, our BoTorch Ax Bayesian optimization has 2 parts. First, SOWAL, which is a Cauchy random sequence, uniformly initializes our model, and it specifically considers previous points to avoid clusters and gaps that may otherwise skew our output. Then a model called BoTorch emulates the unknown underlying functions using a surrogate model, and an acquisition function guides where that surrogate model updates, and the two iterate back and forth. So let's look at this iterative process more closely. So this blue line here represents a true function, and let's revisit our cake analogy and define this function as how the taste of a recipe on our y-axis changes with altering recipe ingredients on our x-axis. So the dashed line is our surrogate model prediction, and it has an associated uncertainty band with it. And at the outset, the surrogate knows absolutely nothing about how good recipes truly taste, so it doesn't emulate it very well, and it's very uncertain. But let's say we do a little research on recipes and how tasty they are, and we develop a prediction for any given recipe. And let's use it on a random recipe in the design space to get the model started. We have just queried an initialization recipe, and now the surrogate knows the true tastiness of that recipe without doubt. Now, there are still other areas in our search space where the model doesn't know how tasty recipes are, and this is what the acquisition function looks for to identify the next query recipe. The surrogate then uses the taste predictor to update itself at that query recipe informed by the acquisition function. This is an example of what that update could look like on both the surrogate prediction and its uncertainty. And we note that the surrogate retains information about the previous query, so now it knows how tasty 2 recipes are instead of 1. We also see that the uncertainty band updates as well to reflect a new confidence over the search space. So with every iteration, the acquisition function chooses which recipe to predict the taste of next. And specifically, it has to balance getting new information about an unknown part of the search space and getting additional information about a promising part of the search space. So this is an example of the former, which is called exploration. The surrogate learned about new areas of the search space, and you can see that by the relatively wide spread of query recipes. Getting information about a promising area of the search space is known as exploitation. This is an example of that, and you can see that there's a concentration of queries around the area with the most delicious recipe, because that's what we're looking for, that's what we want. So this mini example shows us that with each new query recipe from the acquisition function, the surrogate becomes better informed and improves its emulation of how delicious cakes are. When we translate this to sustainable aviation fuels, query recipes become distinct fuel blends, and our taste predictor becomes a property predictor. Now, because we are specifically using Bayesian optimization, we can black box our predictor in that the inner workings of it are independent of our optimization itself. So we can make it a very modular thing, and we can substitute predictors at will depending on what we're looking for and what suits our needs. So for example, we started working with a linear by volume property predictor, and this is pretty rudimentary. It's just a linear combination of each component's individual property value and its volume fraction. But we also wanted to explore a more robust way to predict properties for fuels. So our collaborators at Berkeley Lab developed a data-driven predictor. I'm not going to get too far into the details on that because my collaborator from Berkeley, Anna, over there, presented this work at SciPy last year. So if you have questions about that, you can go ask her later because that's beyond the scope of what I'm discussing today. But as a brief summary, they measured infrared absorbance of fuel samples as Fourier transform infrared spectra, which is what I've included as an example on the screen. And they used those spectra data to train machine learning, a machine learning property prediction model. And that is what I apply here in my optimization work. So to recap, we use target property values and possible fuel components to identify an optimized blend and predict its expected properties. And we do that by first reducing the search space to a best performing component combination, and then find the optimal blend ratio of that combination with a multi-objective optimization. So now we get to have a little fun with it and see what we can do. So we first used the basic linear by volume property predictor, and we examined the boiling point and flash point of a simplified Jet A fuel called a surrogate. And we specifically optimized for the squared difference between the boiling point and flash point of Jet A and the boiling point and flash point of our optimized solution. We also made sure to use the same components as a surrogate from the literature to just kind of do a baseline comparison and see where our tool is landing. So our optimization returned this solution set, and we identify the red square as the solution with the smallest trade-off between boiling point and flash point. We also note that our red square solution lies below the blue star, which represents our literature surrogate. So this indicates that when optimizing for only boiling point and flash point, our methodology returns a surrogate that performs better than the literature with the specific components. However, our optimization only considers boiling point and flash point, whereas the literature surrogate is more comprehensive. So that is what likely accounts for the differences between the two. However, nevertheless, this is a positive indication that our tool behaves as intended, which is very exciting. From here, we gave our tool some design challenges. Now, everything else that I'm discussing today uses our data-driven predictor from Berkeley Lab. We first asked it to just create a 3-component fuel blend from any of the species in this list. We optimized for the 5 properties at the target values given in the table. And the solution we got was a blend of 18% cumin, 21% methyl cyclohexane, and 61% hexene. And the plus minus row in the table shows that the blend generated by our tool was reasonably close to the given target values. So that's super exciting because we got a viable solution even despite reducing our search space down to a single component combination. For this case, we did choose our target values arbitrarily, so let's explore something different. Here we mock a more real-world scenario. So we used Jet A properties as the target values to emulate creating an immediately usable fuel. And I use the words mock and emulate very specifically because the components in this possible list are not representative of what would actually be used in a real jet fuel. This is just what we had the data for to develop our property predictor, so we're a little limited in that scope. Sustainable aviation fuels are also only approved to fly when mixed with Jet A, so we wanted to force Jet A as a component with a 75% maximum. And then we also wanted to demonstrate some more variability with input parameters, where we added a fuel blend as well as molecular additives, and we also wanted to find a 4-component optimized blend instead of 3. So the solution we get with this scenario is 74% Jet A, 8% a 60-40 heptane isooctane mix, 8% tetralin, and 10% cumin. So in this graph, Jet A property values are the blue circles, and the bars are acceptable ranges for the property as given by ASTM. And if a bar extends off the graph, it just means ASTM only provides a one-sided limit. So our optimized blend is the red squares, and you can see that it satisfies our property requirements. So that's really exciting because we were able to find a suitable blend for the given target values we gave our optimization. We do note that we are close to the threshold on acceptable ranges for our melting point. We could take steps to make that not quite as close to the threshold, but that comes at the risk of it being at the expense of another property. That's just the way it works with conflicting objectives and trade-offs between them. This design challenge also tells us that our tool is most useful with a large data set of characterized fuels and fuel species. And again, it was difficult to do a more realistic scenario just because of the limited data that we had to work with. But in summary, we developed a multi-objective, multi-parameter optimization approach, and we designed this tool for variability. We can vary the number of components, both on the front end in the number of possible components we're including as an input, and also on the output end where we can specify the number of components to include in our optimized blend. We also included flexibility to require a component and limits at which to restrict that. And then we also include variability by making substitutable predictors. This work also expands feedstock to function capabilities. This is a digital tool designed to enable faster bioprocess optimization and startup. It has the property prediction that I talked about, developed by Anna and Berkeley Lab, but it also has linked life cycle and techno-economic analysis tools for production pathways as well. And so we can look at designing sustainable aviation fuels at all levels, just from the optimization and then also to production and greenhouse gas emissions. For more information on feedstock to function or to explore its tools, the QR code links to the below website. Thank you.
Mike, thank you so much, Ali, for a great talk. Are there any questions from the audience?
Hello, thank you for the great talk. So you're using Bayesian optimization based on Gaussian processes. Is there any way that you can encode some physics you know about how these materials interact into the hyperparameters and covariance in your Gaussian process?
So when you mention physics, is that the molecular physics behind how the chemistry behind the jet fuels and how those interact? So that gets into the property predictor. Theoretically, it would be possible to include that in a Bayesian optimization, but that's we have made choices not to go that route because of how complex that chemistry is. And that's why our property predictor is using spectra data to do that. And it's machine learning off of spectra data in order to make sure that we can encompass as much of those really complex chemistry interactions we can without fully understanding and being able to characterize those with kinetic chemical models and things like that. Does that answer your question? Yeah, thank you.
Great. Thanks for a great question. Anybody else in the audience? I'm going to look at Matthew, see if there's any questions from Slack. All right. Oh, we got one audience question.
Yeah, hi, thank you. Oh, God. Yeah, just a really simple question. Have you had any feedback from major engine manufacturers on anything that you presented here?
While being here in Tacoma specifically, no, not yet. It also is day one, and it's the very beginning of it. So ask me a little in like a day or two, maybe that'll change. As far as large commercial stakeholders, and that is currently what our research project is really working on getting involved right now. There's V and Anna and Berkeley are looking at communicating more with commercial companies and more like not research developed stakeholders that would be interested in this tool. So that's ongoing.
Awesome, thank you. All right, I have a question. Do you have any advice for researchers who want to start using Bayesian optimization in their work? Are there any like hurdles you overcame or any kind of rules of thumb you learned during this process?
That's a great question. It took me a hot minute to become really familiar with the inner workings of Bayesian optimization and how it functions and all the different ways that you can alter and toy with the Gaussian process mentioned earlier and the acquisition functions. So that is, I would think, very important when starting with Bayesian optimization, is get a good understanding of what it is first. And then it's also really important to understand your problem and the constraints and requirements that you need to use and what you need to consider before even starting to bring in the Bayesian part of it. So.
Any more questions? If not, then let's please thank the speaker again. Thank you very much.